In this work, we introduce Lucid Games, an online inverse dynamic game algorithm that enables adaptive trajectory prediction and planning. Existing game theoretic planning methods assume that the robot knows the objective functions of the other agents a priori. But in practical scenarios, this is rarely the case. Lucid Games solves this inverse optimal control problem by recasting it in a recursive parameter estimation framework. It uses an unscented Kalman filter to iteratively update a Bayesian estimate of the other agent's objective function parameters, improving that estimate online as more data is gathered from the other agent's observed trajectories. The algorithm incorporates those estimates online into a receiving horizon game theoretic planner. For clarity, we only present the two-agent case. We parameterize the objective function of the agent interacting with the robot as a sum of features weighted by a vector parameter theta. To update the belief of a theta, we sample sigma points from the current belief. A sigma point is a guess over the objective function of the other agent. For each sigma point, we solve the dynamic game and extract the predicted state of the system at the next time step. Then, by comparing these predictions to the actual state, the filter increases the weight of the guesses that were accurate in their predictions. Finally, the robot plans its trajectory and predicts the trajectory of the other agent by solving the dynamic game using the mean of the Gaussian belief of a theta. This algorithm is trivially parallelized across the sigma points and reaches update rates of about 40 Hz for a 3-agent scenario. Lucid Games can estimate the desired speed, desired lane, and the aggressiveness level of the agents in its surroundings. In addition, Lucid Games allows the robot to better predict the trajectory of the other agents by leveraging the information gained over their objective functions. We demonstrate this in 3 autonomous driving scenarios. We compare our algorithm to 3 other baselines and show that Lucid Games converges to a trajectory prediction error very much comparable to the one obtained with the Oracle. Additionally, we implement a robust trajectory planning scheme for the robot that accounts for uncertainty in the objective of the other agents by enforcing safety constraints. These constraints are computed by fitting ellipses around the trajectories sampled by the UKF. They act as inflated collision avoidance constraints. In this example, at the start, the robot slows down to avoid the uncertainty-based collision avoidance zone, which comprises 2 possibilities. Either the human cuts in front of the robot, or the human yields to let the robot go first. Then, by observing the human's behavior, the robot better estimates his objective and narrows down the collision avoidance zone to the first option. The results we obtain from Lucid Games are promising, as they seem to let the robot rapidly improve its trajectory prediction accuracy by estimating the objective functions of the agents in its surroundings. We have made our implementation of Lucid Games available on GitHub. Finally, I want to thank my co-authors and advisors at Stanford and CMU, and thank you for watching.